Hi, I'm Peter, and this summer I worked on STM with Professor Sarah Burke, particularly on cross-sectional STM. Oh, there we go. So first of all, what is STM, or scanning tunneling microscopy? So it's essentially a non-optical imaging technique where you can achieve subatomic resolution on materials that you want to image. So the way that it does this is instead of using light, you use a very small tunneling current between a very sharp tip and the sample that you want to image. Now, this tunneling current is only allowed because of two things. The very short distance between the tip and the sample, and the fact that quantum tunneling allows for electrons to jump from the tip to the sample and vice versa. So using this method, you can get an idea of the topology and even get a look at the atoms in the sample, analogous to how somebody could get a mental image of an object by feeling it with their hands. So this summer I used a room temperature STM, which has the advantage that it has a much faster turnaround time. So I can get a sample in, do some scans and get an idea of what the sample is like, and then get it out quite fast. And this makes it really ideal for taking a look at samples and seeing whether they're really scannable and whether they're of high quality and worth taking more precise measurements in a bigger, much slower machine. So using this room temperature STM, I examined samples of deposited molybdenum disulfide flakes, lab-grown iron selenide crystal, intentionally patterned gold, and germanium cross-sections with the goal of eventually being able to image cross-sections of all sorts of materials. And this last one here, the germanium cross-sections, is what I spent probably the majority of my time this summer on. So here's a great topographic image of molybdenum disulfide flake. And we can see here that there's the gold in the background, and it looks a little bit different than the very flat molybdenum disulfide flake, showing you the capability of the STM to image different materials. And here we can see a little line profile, and the height along this line profile is given here. So this tells us that the flake is about 8 nanometers tall. So as I mentioned before, I also looked at lab-grown iron selenide crystal, and some spots weren't so great. So they were really blotchy and really didn't have very many flat areas where you can just get a look at the periodic atomic structure. But some spots were very flat, and when you zoom in, you can actually see atomic corrugation. So this periodic pattern is actually from a periodic arrangement of atoms, and it has the spacing that you would expect in an iron selenide crystal. I also looked at intentionally patterned gold, and we actually didn't think that this patterning technique would work the first time, and we didn't think that it would be very easy to see under the STM. But I actually scanned it and found quite the opposite. As you can see, you can pretty easily make out a lot of the patterns here. But mainly, the main focus of my summer and this talk was cross-sectional STM. So here's a little diagram with substrate and a sample that was grown on top of it. And kind of the end goal, as I briefly mentioned before, of cross-sectional STM would be to scan this cross-section here so that we can get a look at the interface from the side. So why do we want to look at interfaces? Well, interfaces are a great playground for a lot of really cool and interesting physics. So one example is between these two oxide materials. At the interface between them, so where they're bonded to each other, it actually shows a completely different behavior than the two materials. So the two materials themselves are insulating, so they don't conduct any electricity. But if you cool down the interface enough, you can actually make it superconducting, meaning that it conducts electricity with zero resistance, which is completely different from the insulating behavior of the two oxides. So this is just one great example of the kind of weird, bizarre physics that you can get interfaces, and hence studying interfaces is quite interesting and something that we want to be able to do with STM. So let's rewind a bit and talk a bit about some of the more specifics of how we scan samples in an STM. So one way that we usually prepare samples, especially layered samples, this works particularly well with, is we will epoxy a post on top of the sample, and then in vacuum, we will kick off this post to reveal a fresh surface. Now, the key with the fresh surface is that it's not oxidized. So we can get a look at the actual material itself, and we don't have any problems with the oxidized material potentially being insulating, which would not work very well with STM. So we can use a similar sort of technique to try to get a look at interfaces that are not oxidized in STM. So here I've got a little sample holder with a substrate and sample, and the idea that we had at first would be to knock off the end of this just like a cleave and expose the cross section here so that we can get our tip and scan at the interface between the sample and substrate, or potentially in the future between multiple samples grown on top of each other. So in the specific room temperature STM that I worked with, we had a sample holder for cross-sectional samples, which looked a little bit like this. So we have a substrate here or a sample, and then we have a little chip that we would screw in to make sure that it's tight and stays put. And if we look at a side view here, we can make a small notch or something like that and knock it off to cleave it, where the tip would come in here and scan it from the side. So the first way that we tried to cleave it was just by etching it with a diamond scribe. So just really making like a very small cut, just a scratch, and then hoping that if we knock the crystal, which in this case we were using germanium, hoping that if we knock the crystal, it'll naturally break or cleave along its natural crystallographic plane. Now we can see here from these images that this didn't really work out too well. So we've got a very blotchy surface here with not many flat terraces where we can actually get a look at the atoms. And as we can see here along this line profile, the whole surface varies by around 10 nanometers, which is 100 times the general scale of atoms at an angstrom or a tenth of a nanometer. And you can see another example of a very blotchy surface here. And if we try to zoom in on these surfaces, as I talked about before, we just kind of get more blotchy structures and then eventually some sort of curved topographic surface, but we don't really get a look at flat layers of atoms like we want. So to try to improve this method, what we did was we cut through the sample with a wire saw. So I usually cut through this germanium substrate here as an example. I usually cut through around 1/2 to 3/4 through. And then I would put it in the sample holder around here and knock this part off. So here we've got an example of a cleaved crystal under an optical microscope. And we have the sample holder here, sample holder chip that we screw in here. And then we can see the wire saw cut is along here. And the cleaved area, the really shiny bit, is along this part. So this part didn't really cleave so well, but we can see here, at least optically, we can see that there's these terraces almost, these steps, which is encouraging because if there's steps, it most likely points towards in between the steps, we have these flat surfaces. And now we don't know what it looks like atomically, just from looking at an optical picture, but we can hope that on the atomic scale, it cleaved somewhat similarly to how it cleaved under a microscope. And we can see here also at the edge, maybe some sort of steps and then terraces and stuff, which is definitely encouraging. So I got one of these and cleaved it in situ in vacuum, and then imaged it with the STM and actually got an image of germanium cross-sectional atoms. So we can see here a surface reconstruction of germanium atoms. Now, a surface reconstruction is essentially just when open face of the material is exposed to vacuum, so it's not going to oxidize. And because this material is extremely reactive, what will happen is that some of the atoms will move closer to each other, some of them will move farther away from each other, and give you these interesting surface reconstruction patterns. So here we can see from a different paper with a more precise STM, a surface reconstruction of germanium. And the key thing here is that these two look quite similar. We've got these kind of strands and maybe like more open bits here, and it's very similar to what we'd expect from cross-sectionally cleaved germanium. So if we zoom in here, we can get a little closer look at the atoms, and we can see that along this line profile, it all ranges within around 10 angstroms, which is really good because the germanium lattice constant is on a quite similar scale. And now the lattice constant just being the spacing between groups of atoms, more or less. So without further ado, we just had Ko's group grow a thin film sample. In fact, actually Dante grew the sample, so thanks to Dante. We had them grow a 35 nanometer thin film sample on top of a germanium substrate that was previously cut by the wire saw. And then we cleaved it in situ and tried to image the interface. So here you can see a picture of the setup with the tip scanning very close to the interface, substrate here, and the sample holder chip below it. And then the thin film is just on this side. And we can see that this is just a scan of the germanium close to the edge. And we can see that it looks quite similar to our previous zoomed in image of a surface reconstruction. And to corroborate this, we can see that the line profile is all within about 8 angstroms, which for this scale of picture is pretty good. It means that we have a reasonably flat surface. However, I actually wasn't able to find the interface for a few reasons. So for one, it was a little bit hard to tell when I was completely off the sample, because scanning the sample holder chip, which is definitely just oxidized, not very great metal, looked very similar to a lot of the bad germanium cleaves. And also, when I was close to the edge, it was hard to tell when I'd fallen off the edge, which would indicate that I'd found the thin film and I could move back to try to find the interface. But the reason that it was hard to find this was because the substrate cleave was actually slanted. So the depth difference between over here and the sample holder chip was not very great. So a lot of the times it would look like maybe the tip falls off, but then it stabilizes, and it's very likely, or at least it's potential reason that this small difference here definitely contributes to that. So to sum it all up, cross-sectional interface scanning is possible. We can prepare samples in such a way that we can get a clean look at the atoms in a cross-section. But if we want to scan interfaces, we have to make finding them under the STM, purely from STM images, especially considering the kind of camera capabilities of some of the more precise STMs. We have to make finding this interface easier. So one idea that I came up with in discussion with the group was to actually get a gold sheet and epoxy it onto the sample holder chip, and then maybe press it so that it's flat with a hydraulic press, perhaps. And then this way, we can know when we're below the interface, because we can see that what we're scanning has different properties, because gold would hopefully at least have different properties than the substrate. And this would be a very easy way of telling when we're far below the interface. However, atomically, it's worth noting that there would still be a difference between the film and the gold sheet. But this would actually be good, because it would be a bit more of a strong indication that we've found the edge with some sort of dip, most likely. So with that, I'd like to finish my talk and give a special thanks to the Splurebussen Quantum Matter Institute and UBC for hosting my stay this summer, and also to NSERC for providing the funding for my research this summer. And I'd also like to give a big thanks to the Lair group for making my stay really welcoming and a great learning experience. So thank you.